This video will document my attempt at making a Rubik's Cube optimal solving program. My interest in twisty puzzles began 5 years ago. After so long, I wanted some project to demonstrate what I had learned, and felt I had enough programming knowledge to create this. Most of the mathematics I reference come from Herbert Kosiyama's webpage, in his program Cube Explorer, which contains a minimal move and optimal move solver. That's not to say I redid his program. A lot of my implementation is very different than his. And with Cube Explorer being the only publicly available optimal solver, some of my implementation will be, at least, novel. Since Kosiyama's webpage is basically the extent of my formal education in cube mathematics, please excuse me if I restate or reinvent something which already exists. This is just some information that I wanted to include in the presentation but had no good place to put it. Before I talk about the optimal solver itself, it's necessary to discuss the mathematics behind cubes. A set is a concept in both mathematics and computer science which contains elements that are unordered and without duplicates. A map is two sets, with every item in the first set pointing to an item in the second set. The goal of an optimal solver is to, when given a cube state, produce the scramble of the smallest amount of moves able to solve it. An optimal solving algorithm could consist of a map of the set of all cube permutations with pointers to each permutation's optimal solve. The problem is that these two sets are much too large to be stored on any computer, so we'll actually have to be clever about how we program. As the two parts of the solver, I'll now discuss scrambles in cubes individually. There are 6 faces on the cube: front, up, right, back, down, and left, and 3 different types of moves per face: clockwise, 2 times, and counterclockwise. Thus, there are 18 different possible moves. Moves are notated with the first letter of their face, so F, U, R, B, D, or L. Then nothing to indicate a clockwise move, a 2 to indicate a 2 times, and an apostrophe to indicate a counterclockwise move, which I might also call prime. So this would be F, this would be U2, and this would be R prime. We can change any scramble to a list of integers by assigning each of the 18 moves a number 0 to 17, seen in the chart to the right. However, we can do a bit better by realizing that after the first move, there are only 15 options, because it will never be optimal to move that face again. If the first move was U, a second move of U, U2, or U prime wouldn't make any sense, since that could have been accomplished in one move. We can create a compacted list from the integer list by subtracting 3 from any value if the value before it is less than it. For example, below you can see a scramble first in string form, then in integer list form. To convert it to compacted integer list form, we would start with 0, the first move, and add it to the list. The second move, 3, is greater than 0, so we subtract 3 from it before adding it to the list. 13 is greater than 3, so we subtract 3 and put 10 into the list. 8 is less than 13, so it is put straight onto the list, and so on. From the compacted list, we can create an integer representation, which is just a single number. That is done by treating the compacted list as if it was a single base 15 number. The final step is to add integer.min value, which is -2 to the 31. This is done for a pure comp sci reason. The size of these integer representations are going to get very large very quickly. So large, in fact, that they exceed what Java can store as an integer. So if we add -2 to the 31, which is the smallest number Java can store, it effectively doubles the amount of scrambles able to be represented. Now for a lesson on cube theory. A cube has 20 pieces. There are 8 corners and 12 edges. To fully define a cube, all the pieces must be fully defined. This is done with the use of coordinates. A coordinate can be whatever, as long as it defines some aspect of the cube. The 4 most common are corner orientation, corner permutation, edge orientation, and edge permutation. Permutation is the location of the pieces on the cube. When any move is applied, the permutation of 4 corners and 4 edges are changed. Orientation is a bit more tricky to define. As you can see, a piece can be in the proper permutation while still being unsolved. A corner has 3 possible orientations: solved, rotated clockwise, and rotated counterclockwise. That move, by the way, is called the corner twist and is definitely not allowed. An edge can either be solved, like this piece, or swapped, like this piece. Orientation can be expanded to permutations outside a permutatively solved piece. For corners, we can look at just yellow and white stickers. For this corner, its yellow sticker is located clockwise from the white face, making it have a clockwise orientation. For edges, we can say that the edge is properly oriented when the piece can be solved without using the U or D face. This piece is oriented, because if we perform F prime L prime, it will be solved. But if its orientation is like this, it will be swapped, since F prime L prime will make it swapped in its correct slot. Solving it must require a U move. Note that this definition of edge orientation runs slightly counter to the definition used by most cubers, which defines it around the F and B faces. I chose this definition of edge orientation so that both edge and corner orientation would be defined around the same faces. These four coordinates fully define the cube, which means that if all these coordinates are solved, the cube must also be solved. It also means that any other coordinate can be generated from these four base coordinates. A symmetry is identifying mathematical similarity between two different cubes. For our purposes, there are three rules that symmetry must follow. We must be able to control and undo movement between symmetries. A symmetry must be able to be applied to both a cube and a scramble. And finally, and most important for our cause, all cubes within the same symmetry group must take the same amount of moves to solve. The type of symmetry implemented in cubic optimal is rotational and mirroring symmetry. Rotational symmetry is changing the definition of the U and F faces. Throughout this video, I've been holding the cube such that white is on the U face and green is on the F face. If I were to rotate the cube like this, orange is now on the U face while green is still on the F face. If I were to perform a move L prime onto a cube with white U and green F, then L prime onto a cube with orange U and green F, you can see that these two cubes are mathematically identical, although being actually different. Mirror symmetry is done by mirroring the cube across the right face plane. Here, L prime is identical to R performed on another cube. There are 24 options in rotating a cube and 2 options in mirroring, giving cubic optimal 48-way symmetry. If we look at a piece's orientation before and after rotation, we see that it might change. This corner, for example, is oriented, but performing this rotation and redefining U to be orange, we now see that it is oriented counterclockwise. In general, for a corner, a piece's orientation will change when it is outside of its group, a grouping all the corner slots it can reach with just 2 times moves. There are 2 groups, these 4 corners and these 4 corners. An edge may change orientation when it is outside its solved slice, which is the group of edges between 2 faces. This nuance is accounted for in what I'm calling rotational corner and edge orientation coordinates, or RCO and REO. We've talked about coordinates as abstract mathematical objects, but not pinned them down per se. Indexing is the process of assigning each coordinate a numerical value. Indexing must follow a couple rules. Each coordinate within the set of its type of coordinates must have a unique value, and the coordinate with value 0 must be the solved state. I'm not just going to discuss how indexing is done on each of the 6 coordinates implemented, since each one is unique, but this process will be very important in the optimal solver. Below, you can see the size of each of the coordinate types. As you can see, there's a large range in the size of the coordinates. Now we can finally discuss the program. The scramble class is the implementation of the mathematical scramble object. A scramble object is stored as a linked list of integers, using the base 18 definition. As described in the mathematical discussion of scrambles, they can be represented as a single integer. This is done with the toInt and fromInt methods. 2 notes with this. Firstly, when using fromInt, the length of the scramble also has to be specified. This will turn out not to be a problem. Secondly, an integer list is used because for scrambles over length 8, a single Java integer, which is 2 to the 32 bits, cannot store the whole scramble. We solve this problem by breaking up the scramble into 8 move chunks and storing it into an integer list. The iterate method will turn out to be very important. It has the effect of moving the number returned by toInt up by 1. It also returns the scramble, which is used to move from the first scramble to the second. So for example, if the first scramble's toInt values is this, iterate will change the scramble to this. And now you can see the toInt value is 1 higher. It will return bd prime, since this is the difference between the 2 scrambles. Here's the code for toInt, fromInt, and iterate. I'm not going to go over it, but here it is. The cube class has 4 instance variables, representing the 4 base coordinates discussed earlier. All of the coordinates are implemented as lists of integers. To numerically define permutation, we can give each piece a number 0 to 7 for corners, 0 to 11 for edges, as well as each slot a number. Now permutation can be thought about as a list of numbers 0 to 7 or 0 to 11, with each number representing a piece, and the index of that number representing the slot. The ordering of the corner pieces is this: 0, 1, 2, 3, 4, 5, 6, 7. So, for example, if we perform an F move, we can say that the 4 corner is in the 0 corner slot. Corner orientation is implemented as a list of 8 numbers, indices still representing slots, and the number representing the orientation of the corner in that slot, 0 being oriented properly, 1 clockwise, and 2 counterclockwise. Edge orientation is similar, but with a list of 12, and each piece either being 0, oriented, or 1, swapped. Methods for moving coordinates and rotating coordinates must exist for all 4 instance variables, but don't need to exist for RCO and REO since they are derivative from those 4. The toInt method performs the indexing discussed earlier, and the fromInt method's the opposite, creating a coordinate from the index. These 2 methods must exist for every coordinate implemented, including RCO and REO. Here's the code for the described methods just for corner orientation. As you can see, move and rotate are fairly complicated, but toInt and fromInt are fairly simple. Now that we have the tools of iteration and coordinates, we can imagine a simple optimal solver. Here's a basic diagram representing the tree of scrambles. All it does is start at the first scramble of length equals 1 and check if the cube is solved. Most likely it won't be, so it will iterate to the next scramble and check again. If it reaches the end of a length, it starts again on the next length. This approach would work, except that the size of the scramble tree is much too large. I drew the tree as expanding linearly, but in reality it expands by 15 times per moving to the next length. This will be the basic approach to our solver with the addition of one other trick. Imagine we had the ability to take a guess at how many moves to solve would be, the only caveat being that we are playing by Price is Right rules, highest preferred but can't go over. We will call this guess the pruning depth. Well, if we know that at a certain point the cube is at least 5 away from being solved, on our scramble tree we can rule out all scrambles which derive from the first scramble and are less than 5 moves away. We will no longer have to iterate across and check them. Using this strategy, we can rule out large swaths of the scramble tree without checking every single item. Another way to think about it is we are ruling out multiple scrambles with every check. So how do we come up with this guess? Although the set of all full cubes is unreasonable to fit onto a computer, individual coordinates can fit, and it is possible to create optimal solvers just for those coordinates. What we can then do is create a map of all coordinates to their distance to solved. Now, if we know that corner orientation must take 4 moves, the whole cube must therefore take at least 4 moves. If we are analyzing multiple coordinates, then the largest distance is the taken pruning value. Sets for corner orientation, corner permutation, edge orientation, and RCO are small enough to fit onto the computer directly, but for larger sets, we are going to have to reduce their size by symmetry. This is where the third rule of symmetry comes in. All cubes with the same symmetry will have the same amount of moves to solve. Reduction by symmetry is done in the following way. We take the coordinate in question and rotate it 48 times and find the smallest value of those rotations. This will be called the identity coordinate. A raw-to-sim table contains a list of all identity coordinates in ascending order. The index of a given identity coordinate in that list is the sim coordinate, and what will be used in place of the raw coordinate done in non-reduced tables. Reducing by symmetry is a trade-off between computing time and memory, which is why in the final implementation I give the user the ability to pick if they want to use symmetry reduction or not. And now we can finally see cubic optimal in action. To run the program, open command line and cd to the location cubic optimal is saved. Then cd bin and enter Java solver. When the program is first started, it will ask you to enter a suboptimal scramble as a way to generate the cube being solved. If you have a cube permutation but not a scramble, I would recommend using Cube Explorer, which has a graphical interface, to generate the scramble. Here, I'm entering a scramble of length 7. Hitting enter will prompt you to enter the coordinate tables you wish to use. You may enter as many as you want. Entering more will give you a higher chance of getting a higher pruning value, since the highest distance value is what's taken as pruning value, but will be a bigger drag on the computer. You are also given the ability to enter each of the 6 coordinates as either symmetry reduced or as raw coordinates. For this solve, I will use corner permutation, edge orientation, and RCO all as raw values, and enter 0 for the solver to begin. If you enter a table which you don't currently have, the program will create that table before beginning the solve. Note that the larger tables, EP and REO, can take a very, very long time to come to completion. That quick jump from length 1 to 6 is the solver instantly throwing the pruning depth to 6 and skipping over scramble length 2 to 5. And after a while, it will produce an optimal scramble, which we can see is of length 6. Performing the suboptimal generator scramble, then the optimal solving scramble, and getting a solved cube, we can see that the solver does work. As stated before, Cube Explorer is the main publicly available optimal solver, and what the math of this program was based around. Still, there are a lot of ways this program is different from Cube Explorer. My implementation has multiple different coordinates and tables available to be used, and lets the user choose from a variety of coordinates, while Cube Explorer only has one type of coordinate, seen here to the right. Cube Explorer only has reduction by 16 times as a result of the coordinate it chooses to use, while all the coordinates in Cubic Optimal are reducible by 48. However, the major difference is that Cube Explorer, at the time of this recording, works. Cubic Optimal only works limitedly right now, and I would not attempt to solve over 8 moves long. This is a result of the smaller tables that currently exist, which leads to smaller printing depths and its overall slower performance. Which brings us to the final slide. Cubic optimal is still very much a work in progress. There are a lot of places where the programming is suboptimal in a computing time or memory sense, but I glossed over for the purposes of getting something finished. I know individually where those places are and what work can be done to improve them. Beyond that, in looking to improve the program, I would like to introduce even more coordinates and table types. I designed the program such that expanding to more table types should be easy. All that has to be done is adding the indexing to int and from int methods in the cube class. However, currently for symmetry reduced coordinates, the coordinate must be fully 48-way symmetric, which is limiting, and I could find a way to introduce coordinates with less symmetry. Another improvement would be the addition of a graphical user interface, much like the one in Cube Explorer, so the user can directly enter a cube permutation without having to create a suboptimal generating scramble. This concludes my overview of cubic optimal, my attempt at a cube optimal solver. Thank you.